Hello, everybody. Welcome, welcome, welcome to the Jacobs School of Engineering, to the UC San Diego campus, to Franklin Antonio Hall, to the Bob Kahn Executive Outreach Center, and to this special roundtable discussion with our wonderful, wonderful guest, Professor Carver Mead. My name is Al Pisano. I'm the Dean of Engineering here. I've been participating in the Kyoto Prize, hosting the Technology Laureate for several years, and believe me, Dr. Mead, I am so honored, Professor Mead, so honored to be helping this afternoon with this as well. So it's a very simple format. I want to say that we have given everyone a QR code so you can submit questions. Many people have already submitted questions. Andrew Kahng here has the tablet where they appear, and of course, if 3 questions sound alike, we'll ask it once, not 3 times. All right, now to the formal opening of the program. My job here is very, very simple. Aside from thanking Dr. Mead again for spending some time with us, my job is to introduce our moderator, Professor Andrew Kahng. Andrew Kahng is a distinguished professor of computer science and engineering and electrical and computer engineering. But better yet, he's a UC San Diego alum. All right, that's the part I like. Dr. Kahng holds the endowed chair in high performance computing. He heads up UC San Diego's VLSI CAD lab, and he's on the executive committee of the Marco Design and, I'm sorry?
That's about 12 years old.
Okay, so, all right, so let me correct myself. When Professor Kahng was only 12 years old, he had already reached the executive committee of the Marco Design and System and drove the roadmap for international technology of semiconductors. So I'm much impressed. At 12, I wasn't doing that. All silliness aside, without any further ado, I turn it over to Andrew Kahng.
Wow. Thank you very much, Dean Pisano. No. So, welcome to this roundtable. It's nominally on the VLSI revolution, echoes and futures, hosted by the Jacobs School as part of the co-sponsorship of the Kyoto Prize Symposium. So we're here to honor and learn from this year's laureate, Carver Mead. The Kyoto Prize was awarded for his pioneering contributions that gave rise to what we look back on as the VLSI revolution. IC design methodology, design automation as a discipline and an industry, the utterly foundational separation of concerns between design and manufacturing, and how VLSI design has been taught to generations of chip designers. And we also have 2 luminaries who also need really no introduction. John Smee is Senior VP of Engineering and Global Head of Wireless Research at Qualcomm. He oversees all of the 5G, 6G, and Wi-Fi R&D projects, including systems design, standards contributions, and advanced radio, hardware, and software research test beds, and technology trials. He's been with Qualcomm since 2000, holds over 200 US patents, and leads Qualcomm's academic collaboration programs across many fields. Sanjay is co-founder and co-managing partner of Snowcloud Capital. I think we all know he spent 14 years at Qualcomm, where he was the chief operating officer and president of Qualcomm CDMA Technologies. He has been CEO and chairman of Motorola Mobility, and then CEO of Global Foundries. So let's please welcome all 3 of these gentlemen. So I'll basically I'll lob these softballs out there and let these folks just take a whack. So the first question that we'll start off with is, especially for the younger folks, what do you see as exciting in semiconductors? When you look out 20 plus years into the future, what makes you excited and thrilled to see happening? Is Carver or
Well, I'd like to hear what the people who are doing it see, and then I can share any insights that I might have. I'm not doing that anymore, and so you have a much more current view of what's going on than I do. So I'd love to hear your take on that.
Yeah, I think it's a great question. I'll certainly give a few opening comments on it. And what's interesting then is when we look at the design targets, the KPIs, it's an interesting thing of targeting different things that are originally was about integration and everything being part of one big chip. And then the realization of the role of the application, so how are you designing for automotive? Think of a very powerful car that's doing more and more functionality. It's going to be on the road for 10, 15, 20 years. So you need to design in a lot of interesting long-term thoughts about what software you might want to be running 10 years from now. And then you go all the way to low-power IoT, and even going to as far as ambient IoT, so super low power, super low complexity. It's almost ambient. It's doing energy harvesting. So this kind of reality, whether you're looking at very large scale or very low cost, low power, or whether you're looking at a cloud data center versus something that's purely mobile. So I think one of the most exciting things is then the use cases are changing significantly. How you design the hardware targets in terms of what are you focused on? Is it energy efficiency? Is it the overall power consumption? The role, obviously the AUC matters in terms of the cost of the product. But at the same time, you're trying to solve almost continually evolving problems, but you have a much more powerful tool chain, right? So we all saw the exciting news with ChatGPT and the ability to have new types of AI algorithms. And I think for the next generation of students entering the field, it's really about how do you combine these new tools with these new targets.
Thank you. First of all, it's great to meet you, Dr. Mead. Before I get going, they're not very often that I find myself in a room with people who have created more than $1 trillion industry. There is wireless and there is semiconductor. And I think that it's worth noting that we have two people present here who have created more than, each one of them more than $1 trillion industry. And I think that's remarkable. I also see we have Charlie Persico. One of the things that has really changed, I think, the way we communicate is the use of CMOS for RF. It's really driven. I remember when cell phones had 3-5 materials in every single component. If you wanted a mixer, you have to have, if you wanted linearity, the only way you could do that was 3-5 material. And the dynamic range needed was about 100 dB, 110 dB, and it could not be done. And I see Charlie. Charlie was, I wouldn't say single-handedly, but certainly he led the organization that created over $10 billion of industry at Qualcomm. So it's worth acknowledging that there are some very successful folks in the room. Thinking about what is where VLSI is headed next, I see further evolution in RF as we go to up to 128 gig of communication, gigahertz frequency for communication. Then I see optical as we go to 300 nanometers to 800 nanometers, and then actually 1.5 micron worth of bandwidth. So I see RF evolving further, particularly with radar, particularly with sensing in an autonomous environment. I see optical. The whole optical computing field is just getting started, and I think that's really exciting. And we know that if optical is going to take off, it'll have to be on the back of CMOS. Now, you can't generate light from CMOS easily. You'll have to have some hybrid 3.5 there, but I think that most of the processing will have to be done in CMOS for it to be scalable. So the RF and optical. Third thing I would say is that I think all the displays will turn into gallium nitride micro LEDs. So you will have acres of silicon square kilometers of silicon being shipped as displays here very shortly as we go towards gallium nitride. Then you're now seeing digital control of all motors. So silicon carbide becomes very, very important because you have to source up to, I don't know, 500 amp of current and control that current in a pretty smart way. And then I think batteries, there's a company called QuantumScape, which is delivering solid state battery and a solid state semiconductor battery. I think batteries are going to, I just don't, I can't think of which part of our life which won't be impacted further by what is happening in semiconductor. And I think that there is a huge concern about lack of scaling, and I'm not concerned about that. I think semiconductor scaling may have stopped, but semiconductor innovation has not stopped. Thank you. Carver, any reaction to these many topics?
I think what you just said is a key thing. We spent our little group at Caltech was doing research on how you make efficient use of silicon back in the 70s. And nobody cared, because if you just got to the next process node before your competitor, you're way ahead of any fancy design that you could do. And that went on long enough that people basically adopted, yes, you get on the next process node when it comes up. And that means just use the design you've gotten, enlarge it and enrich it with the modules you've got, and go to the next process node. And that's a strategy that paid off long enough that people forgot how to think about doing efficient use of silicon, because it was so much more effective to just jump to the next process node. So the things we worried about back in the 70s are now starting to come back in focus. And it's really good to see it. But of course, nobody remembers that we worked a lot of these problems in the 70s. But then, if you look, and by the way, I agree what you said about integrated optics. It is going on CMOS, and it inherently has larger feature sizes than electrons. Electrons are more susceptible to localization than light waves are. And so the things you integrate into optics are different things. For example, there's, you probably all know that there's now possible to build resonators with Qs in the many decimal places. I think the last one I saw was 10 to the 14 or something, I forget. But just phenomenal elements that can be used in wonderful ways. That I wouldn't rule out clever ways of generating light. There were little inklings of that maybe 10 or so years ago, and then that sort of went away. But I wouldn't rule it out.
Coherent light is difficult. Non-coherent, I think people have demonstrated.
Yeah, but you know, there's cleverness to be applied, and I wouldn't. It's not going to be tomorrow, but I think maybe there's something there. Especially since you're putting another layer on for the integrated optics, then there's things that could be And I don't have a specific thing, but it feels like there could be something there. But then if you look further out, we actually do what somebody from another planet would think of as a pretty stupid thing. Because we take a circuit and we hook together transistors with wires in order to make it digital. Well, back in the 60s, when I was working with the Fairchild people, they would occasionally get a return transistor that had what they called popcorn noise. And you'd just hook it up as an amplifier, and it would have this random telegraph wave coming out, substantial current, in the milliamp range. Well, we looked into that. I worked with the Fairchild people, and turned out what was going on is there was a recombination center in the depletion layer of the transistor. They were bipolar transistors back then. And right next to it, there's a trap. And when it would trap an electron, it was a quiet transistor, but then when the electron would go away, there was a little path for recombination. And so you got this recombination rate, which would go on and off, with a single electron. And this was in the 60s. So this was an accidental single electron transistor. So the thing that interesting about that is that this is something that is digital in the silicon, not because you hooked up a circuit to be digital. Now, my old colleague, Ivan Sutherland, is up at Portland State now, and he's got a technology where they use one flux quantum in a superconductor as a natural digital thing in the physics, not in the circuit. And he claims they have a way of doing logic with it and actually transmitting signals on a length of conductor. I haven't, I looked just quickly at it, but suppose that were to work out. They're not as dense as transistors, but they're digital and non, they don't go away. What do you say there?
Non-volatile?
Non-volatile, thank you. In the physics. So that's interesting. Now you have to keep them at low temperature, but in today's world, the MRI business has caused the creation of refrigerators that keep things around 4 Kelvin for months, years, running 24/7. So it's no longer a big deal to keep things at superconducting temperatures. So somebody should look at that. It's a long shot. It'll be 20 years before it becomes a production technology that can compete with silicon in any way. But it's a very interesting story. Now, you have to be careful about how you count power, because power at 4 Kelvin is 100 times more expensive, at least, than power at room temperature. So, but there is an issue there of having the digital part be in the physics And I haven't seen too many people that thought you could make a single electron transistor. And the problem there is not the transistor. The problem is trying to take the signal any distance. So having a transmission line, which Ivan claims they can do with the superconducting flux quantum bits, very interesting idea. And so, you know, if I were looking forward more than 10 years, I would have a little group that was working with Ivan to figure that out, because if there's anything there, there's bound to be a place for it somehow. And energy is certainly a big issue, and it's not really getting much better. So we're, and of course the saying used to be that Andy Grove giveth and Bill Gates taketh away. The new, what people call AI, is really neural networks backpropagation, which was a 30-year-old development, a bunch of it right here in San Diego.
Jeffrey Hinton, yeah.
Yeah. It's largely mindless in its use of power. And there's a lot of things you could think of, but one of the things is that the brain does computation way more than you can do with any of the biggest systems we have. And it runs on 20 watts with slow logic. So you look a little at what's going on there. And the last time I talked about this was at Irwin's retirement party. The dendritic trees of neurons do what amounts to logic in an analog space. They have a very elaborate gain control system. So they actually can sort out, depending on the level of signals coming in, they can sort out basically arbitrary subsets of this exponential number of possibilities. So it's a thing that in its conception is vastly more energy efficient than any other computing structure I've ever seen. And that's not because it's the slow goo that neurons are made out of. It's because it's an idea that is extraordinarily powerful. And I tried making one out of existing technology when I was doing this stuff back in the early 90s, and I was unable to make progress. I don't know anybody that's building one now. Kwabena Bonin at Stanford has some ideas about it, and I don't know how far that's gone in terms of realization. But there are computing structures that we haven't thought of because the transistors have been so damned good. And it's the same trap that got people into the stick with the next process node. They're so good that in the short term you can't beat it. And so then people who think about beating it get weeded out because they're not contributing, because it doesn't get there in time for the next product cycle. Perfectly understandable, but there needs to be some look ahead in terms of computing structures that have in their physics computation that we haven't thought about. or haven't gone far enough with. So,
I think just picking up on that point, if you look at how neural networks are implemented right now, it's using a von Neumann architecture, which is incredibly energy inefficient. You got to go fetch, store, and I actually have a little bit of a sense. I've invested in 2 companies that are using magnetic effects. It actually goes back to your Ivan Sutherland's work in a different way, using magnetic effects where you have a resistor and you can change the value of that resistor as more signal goes through that resistor. And therefore it sort of begins to imitate a dendrite. So yeah, I think it's got to be, there is no way that using the current GPT-4, they're saying has 100 trillion parameters. 100 trillion parameters. There is no way that if they recruited 30% of compute in the world that they could implement, scale that much further. So the compute structure has to change and it has to be physical.
And maybe I'll add a couple points to that comment raised by Sanjay, that when we look now at the on-device AI, to your point on the number of billions of parameters at play, and then we look at the training side, and then we look at the inference side. So the training on huge, massive data sets in the cloud, but then a lot of progress being made on the hardware design, targeting power-efficient AI architectures. So how do you do the quantization? How are you looking at the critical time paths? So a lot of very collaborative, I would say cross-disciplinary research. And I think that's one of the interesting points I think you're making about, you look at the physics side and the semiconductor side, and then you look at the digital side. And what was okay to be separate made sense for a long period of time, economically and pragmatically, but to solve these new kind of problems that are being posed, such as how much AI can I do on a handheld device that's going to charge once a day, when I'm needing to apply more and more AI locally. Then all of a sudden there's this focus on, okay, if power is the primary metric and you're not just chasing things, then you can simplify some of the parameterization. You can simplify some of the quantization and say, I can still achieve very good performance in this kind of reduced state space. So it kind of, in my view, it's an interesting application where mathematicians are involved. We have semiconductor teams involved. We have algorithm PhDs involved. And they're all kind of working jointly to say, okay, we need a better net solution to this really important commercial problem.
yeah, we've gotten to an interesting point where the big networks now, there's a whole lot of power that goes into just using them. Training is off scale, out of control, but then just using them costs a lot of power, and a lot of people are doing it. Terry Sanowski's journal, the latest issue, just came out that has papers by a number of us that sort of look back over 30 years since backpropagation started, and since we started trying to make neurons in silicon. And one of the comparisons I did in there is in the application space where you're just using the already trained network. What happened if you did what you're doing when you just evaluate put inputs to the network and evaluate what it says. What you're doing is you're picking up combinations of analog signals with digital parameters. So what happened if you just go ahead and do it analog? Well, there's a factor 10 to the 4 in energy. And it's not that it's a slam dunk, because you have to get back to where, the technology hasn't been evolved to be good at analog. But then, if you're going to be good at RF, then that's an analog problem. And so we're not because we're not at the point where a single electron is a bit, we're still using a bunch of electrons to make a bit. And then you have the statistics of the bunch of electrons, which you think of as noise if you're doing analog stuff. There's a thing to be worked there, which is worth at least a factor 10 to the 4 in energy, and not that much in silicon area, but considerable in silicon area. So there's rethinking of things when you have something where you have everybody on their cell phone evaluating the neural network. Now power matters a lot more than it does if you have a data center.
Right. I mean, actually the audience supplied 20 questions and we boiled it down to 8 and we're not done with the first. So I'll just sort of nudge this a little bit forward. So if I can summarize, I feel like there's a lot that's exciting. There's essentially beyond everything, as we say. And it's beyond Moore, it's beyond von Neumann. There's the gap between digital and analog, you know, the raw device. There's materials, 2D materials, and so on that looks great. Superconducting, quantum, 3D. Huge stack, really, that is yet to explore. And I feel that the message for younger people is, you know, Moore's law is dead is an opportunity, if you even believe that statement. And so I was going to ask if you had to think of one thing that keeps you awake at night about the future of this amazing industry or domain that's, you know, matured over the last half century or more. What is that thing that keeps you awake at night, if any? Or is it just daisies and sunshine looking 20 years out?
I mean, I'll kind of offer some quick thoughts on that. I mean, for me, it's a little bit, when you're looking at the multitude of problems and the reality of investment and how are you able to tackle something that's economically meaningful and combine that with the long-term foundations, right? So it kind of goes back to the point that Carver made incredibly well about if the next, you know, obvious step is the easiest way to get a benefit, then you don't have to do the harder stuff. And then, so what kind of keeps me up a little bit is then our ability to still foundationally invest in the harder stuff. And so we've been at Qualcomm working very closely with UCSD as a great example on when we look to the future of technology and still doing the really hard stuff that doesn't immediately obviously have, you know, hundreds of billions of applications or consumer scale revenue opportunity. So how do you still do the hard science, the lab coat stuff, the deep simulations when you're working hard at 2 a.m? And so for me, it's a little bit about getting that chemistry right between the foundational research and then coupling that to the future applications. And so there's a lot of exciting, vibrant examples of how the industry's changing, but we still have to keep focusing on the fundamentals because those are the building blocks that will solve the really, you know, I would say more foundational challenges.
If you imagine a value stack in technology and you imagine it as a 20-story building, and there's no question the VLSI designers are in the dungeon and the Google engineers are sitting in the penthouse, right? That, I think, is the fundamental problem in semiconductor. We have not figured out a business model which compensates us for the R&D risk, capital investment. And I think the reason is that we get too focused on solving component level problems and not system level problems. You get rewarded for solving system level issues. And the closer you're to consumer and the end problem, the more you get rewarded. And I think what keeps me awake is right now, if you went to any university, you will have a tough time getting enough graduates who are interested in semiconductor to start research of the kind that Carver really is right to say. We went through this phase where VLSI became completely automated, and you press a button and certain lithography gets printed. Now we have to go back and rethink from ground up, from physics up, a lot of computational structures. We have nobody. We have nobody left to do that work. And I think the reason is because we don't have a business model that rewards them.
And academic reward models, et cetera, novelty. But before passing it to Carver, I want to inject Dean Pisano's online question, which is very related. He asks, how do you see engineering and science interacting and changing one another as we see microelectronics evolving into the future? So I think this speaks to kind of how do we manage this incredible explosion, this Cambrian explosion of possibilities for the near term even, and then the investment question. So
yeah, and I would just say maybe one word answer was the iterative part, right? That science needs to be iterative with engineering, right? So engineering is very pragmatic and science can be very deep. And so how do you get that chemistry of those iterative steps where you're jointly putting things together?
Yeah, but I was talking with Gert Kahnberg earlier today, and he's pointing out that we went through the golden age where we were doing neuromorphic circuits and systems, and we had access to fab, and the fab was easily understood. So the conceptual base was reasonable. It was rich enough to do interesting things, but it was limited enough that you didn't have to do everything all over again, including your thinking about devices, when you went to the next process node. And we went through probably maybe 20 years that way.
Yeah, probably
And,
10 transitions. Yeah.
Yeah, and it was the golden age from a research point of view, because Moses would turn the thing in a couple of weeks or at most a month, and so everybody was actually producing real artifacts and finding out what they really did and realizing that your simulation only got it right a fraction of the time, and there were things that went on that you hadn't anticipated and aren't built into the things about simulation is they tell you all about the things you thought to put in. And the things you didn't think to put in, of course, that's where the bugs always were. So that's a wonderful lesson that we get from real life in those days. And now Gert tells me it's very hard that the getting into fab has to go through some big pile of software that somebody has copyrighted, and by the time you're done, it's very hard to see what's down there and to see how it's related to what you want to do. And so we're in a now as you pointed out, the optical stuff is now at in the golden age that we were in the 70s, and they're doing fantastic stuff. I mean, unbelievable quantum leaps in capability, and that's going to pay off big time. Is paying off already. And much more to come. And it's what you said, the ability to actualize in real physical form the idea that you had, the concept, is priceless in educating students how to innovate. And if you can't do that, you're in the mercy of a big simulator, which is a big pile of stuff that you don't understand, and the limits as to what you can do on the silicon itself, and so somehow that means that the kind of innovation that we're talking about isn't going to happen through that channel. And so I see it happening right now in the integrated optics, just because you have that connection. The same person that has the concept goes all the way to a physical device and tests it and figures out what it's doing. And that connection you can't lose, or you end up with specialists. And you don't do innovation very much with specialists.
On the other hand, 30, 40 generations of scaling literally have resulted in these system complexities that are incredibly hard to manage. So the actualization and the experimentation, I think, is something to worry about, as you point out. So I think this does, if we play back the tape, surface a number of things that actually we should be worried about. And there are challenges to solve, whether it's investment or teaching of young students, and ability to hold things in our hands, which is something that even the US government has highlighted as a national priority recently. There are a bunch of young folks who have put themselves in the back of the room. And some of their careers will last not just 20 plus years from now, but 40 years from now, they will be still in the workforce. If you could give them a blessing or 3 wishes, what would you wish for them? Based on incredibly successful careers and mentoring thousands or hundreds of young people.
Yeah, maybe I'll start with a few comments. I would say one is to evolve, iterate, and grow. So it's really about, are you learning as much as you can from your colleagues as you're contributing and learning? So you get out what you put in. So you have to put in a lot so that you have fruitful engagements, but it's important also to learn broadly. So the opportunity to go deep in school and then continue that depth, but then to broaden yourself in terms of the technology exploration combined with the business opportunity side. And so in my view, it's about really continuing to be a lifelong learner and recognizing that learning does require still the deep technical knowledge. So many of us, I started my career before, and we had AI courses when I was in grad school, and people were like, maybe I'm going to audit that one. It's not super important, to your point on recursive neural networks and backpropagation. It was like, yeah, but that's not really super relevant. I'm going to focus on something else. But you can still learn that at any point. And I think now, even with so much more material being available online, and whether it's, Coursera or whether it's information from recorded lectures, even at UCSD, there's so much more stuff to be a lifelong learner. And so my advice is to be resilient in these kind of challenges that are, and kind of obstacles that are going to come your way, and recognize that those are also these opportunities to kind of learn new things and adapt and kind of keep growing as a person in terms of your approach to it all.
The blessing I would give, as I do my 3 sons, is may your skill set not become obsolete in your working life. If you are a minor in Virginia, learning to code in Python is not that easy to do at the age of 45. And so there's no question, I think it builds on what John said, there's no question that the change in skill set is going to be very, very large. And what we consider to be our skill set is fragile, has a timestamp. And so what John suggests, which is that you adapt, is going to be very, very important. When faced with difficulty, US Army has done a lot of work. 70% of people perform badly, 14% do the same, and 7% actually do better. And there's been a lot of research, people call this positive psychology. Why is it that 7% of people, when they lose job, when they have a car accident, or some loved person passes away, faced with very difficult circumstances, why is it that 7% of the population actually performs better? And I think it's worth, I urge you look into this yourself, but what they found is people who are hungry enough to want to risk and confident enough to actually take the risk, I end up being successful, which actually reminds me of an old joke, which is this guy prays every morning, devoutly, "Good Lord, please let me win the lottery." And he does this for 7 years. One day, the good Lord appears and he says, "Will you at least please go buy a lottery ticket?" So the thing is, you certainly have to have big dreams, but you also need to think about the practical reality of accomplishing that, and the way to accomplish that is to take those risks in life, which are incredibly uncomfortable. I think becoming uncomfortable as a cultural value is going to be important in your lives.
And actually, a few of us have had the privilege of hearing Carver speak to young people at his lecture yesterday and at the banquet last night. But you have a fresh set of faces. What would you wish for them, or what should they be taking away?
It's difficult to think differently. But if you're part of the herd, it's a herd. So the people who are not afraid to think differently have a harder time. And I'm sure that's the 7% you're talking about. But because we face this future which is evolving very rapidly in directions that we can't foresee, which change, I mean, just the emergence of big programs and data sets in what's now called AI, the neural network thing, really changed everything in computing. Not just computing, I see all my colleagues in every branch of science now using those techniques just like you would use any other computer algorithm. It's just a toolbox that's expanded at the cost of a huge power expenditure. There's, in my mind, there's an emerging need for people to think in new ways, but it's not popular. So in a way, being part of that 7% means that it may be generative of difficult circumstances. So
by choice.
That's the trade-off you have, is that if you think differently, it won't be as easy a life as settling into a nice job description. That's where you are, and I think that's the trade-off.
And if I may, there were several inputs from folks who basically asked the same question. They said, "Dr. Mead, what would you tell your younger self?" And it ranged to as you became an assistant professor to as you were a 20-year-old. What would you tell your younger self, if anything, in retrospect?
Well, I can answer a slightly different question,
Okay.
but related question. Mm-hmm. The fundamental things in physics that I've been interested in since I was an undergraduate student, I never felt comfortable putting forth or really working on seriously until I became emeritus. And therefore, then I had the freedom to go for it because I didn't have a downside. And had nothing they could do to me. I think looking back, that was prudent, because I think the reality was that the things I'm doing now wouldn't have been tolerated at all in those days. So it's a delicate thing. I am very pleased with the things I've been able to do, and they certainly have been thinking differently than the herd. And they've been much closer to realization, which has been good because you get the acid test of making it work in the world, and that's a very, very important thing. So I would think that young people would want to be in a applied discipline because you get that feedback for making it work in the real world. And looking back, I think that was a very important part of my evolution in thinking, just the discipline of making stuff work in the world. So if I were you, I wouldn't get caught in a thing where that wasn't part of the equation.
Great, thank you. So the topic today nominally was the VLSI revolution, echoes and futures. So, this is the book, right? I was able to find it, just in this other bookshelf. And I think for most of us in the room, this book was always on a nearby bookshelf, if not on the desk. And how the VLSI revolution was launched by the class at Caltech, this book, and the Moses service that Carver mentioned, the MPW shuttle, is quite well known. And the question is, today, do we need a VLSI revolution 2.0? Is there a different class, a different book, a different service that lets people actualize and touch their implemented ideas? What would that look like if so? I'm sorry if that was poorly worded, but
Well, we're seeing it with the integrated optics stuff.
yes.
It's upon us now, and that's fantastic. It's wonderful, because at least there's one thing that's just going gangbusters. And so we know it hasn't ceased to be that you can have a thing like that. Within the integrated circuit design itself, the innovation has kind of been pushed into the corners because you have this great big thing and it's just chugging away. And it's paid off so many times that you just turn the crank one more turn. And that does not bring forth the kind of innovative energy that you had in the 70s and the 80s. And but we have it now in the integrated optics, and that we had it in the 60s, 70s, 80s in lasers and Amnon Yarev's initiatives that turned into a whole field of quantum electronics, probably the way to say it. That was on a big roll too. So these things keep happening. I think as long as there's at least one of them, so that people don't give up on the concept that there can be a golden age of invention and innovation and realization and real things that then go out and change the world. As long as at least one of those is happening, you can believe that they will be the next one. But when they stop happening and you think, oh, all it is turning this great big crank and it grinds one more time around, you really don't want young people to come to a belief that, well, that was the last one.
Right.
That would be my nightmare.
Yeah.
The thing I would like.
That the base or the foundation is just too accreted and unwieldy to even attach anything to or integrate anything with.
Yeah.
I think that's the fear. Any comments from you gentlemen? Or?
I would say we continue to solve in VLSI. In VLSI, we're wasting huge billions of dollars solving non-economic problems. Going to 1 micron is not an economic, Moore's law was an economic law, and we're spending, the last fab I built was 20 billion. So I think it's just crazy. I think we should be spending our money where we can solve vast number of non-structured problems with, as Carver says, with physical solutions that match the physical properties of what is needed to solve the problem. Packaging is a big place I would put a lot of effort in. I know there's national pride involved in having 1 nanometer on our shores and whatnot. And I understand why that is important in certain applications, and I'm not, it's just that I think it's disproportionately important in just that drug that we've got used to, that drug isn't working anymore, but we're still spending a lot of money on it. I think in magnetic development, in optical development, in display development, in all of these, there are probably 10 different things that I can think of. Arwen and I are involved in a company which is using chips to do separating exosomes. I think biology is going to require a huge amount of silicon design. And what I would like to see is a prototyping facility like Moses, but so that in semiconductor, learning cycle determines the pace of your innovation. Mm-hmm. And what is happening is, look, in 1 nanometer, 3 nanometer, it takes about 6 months to get a wafer back. Well, guess what? You're not going to learn a lot in 1 year. If we could do that in 2 weeks, we can learn a lot. So what I would like to see is prototype centers to allow people to innovate and experiment at low cost in 10 different areas other than just scaling lithography.
You know, it's interesting that Moses still exists. And so there's no fundamental reason why we couldn't have that kind of service that you just mentioned. But it's gotten all of this stuff between the designer and the silicon, and you can't see through it.
Yeah.
I think the hyper consolidation, there's only really 2 fabs, maybe 3 fabs. There's only 2 EDA companies. I mean, the IP and export control and other obstacles are just, and the cost, which I think Gert probably was referring to when he spoke with you. They're absolutely stifling today. So we'll have to obviously solve that somehow. But actually that leads me a bit to this other question that came up, which was that Carver, I think, very famously predicted the emergence of the commercial EDA industry. He also predicted the disaggregated structure into fabless and foundry. And so I checked this morning, Cadence and Synopsys each had a market cap of around $56 billion. And you add them together and you've got the market cap of an IBM or an Intel, or even close to a Qualcomm. So first of all, I'd like to say Carver nailed it decades ago. And second, has the right thing happened? That's the question. Or is some sort of course correction needed on this trajectory we're on to ensure sort of better health of the semiconductor design companies and the manufacturing companies even? Any thoughts on?
Well, you know, for me, there's signs of hope, because there are foundries that do integrated optics, and they do fast turnaround, and they do quality stuff. Who would have guessed? Because integrated optics was a toy when that started, but there was a model from Moses and TSMC and whatever. There's a model of how it can work. And so if it's just a different medium, but there's a model of how the whole thing works, it's a lot easier than if it's the first one, like getting Moses started was, which is, a huge heavy lifting because none of the pieces existed. And so it was, building it from scratch. So I think that's a hopeful sign that we have the notion of foundries is well known, and there are, and for things at the scale of optics, which aren't, these billion-dollar fabs, there have emerged businesses that do that one way or another, and I have no idea how much the government did and whatever the politics is.
For sure. Yeah, the Wolfspeed, Qorvos, the 150 millimeter or 200 millimeter wafer sizes. I mean, you see a lot more agility and diversity available, and it's commercially successful.
Yeah, you can get enough commercial success going that it isn't just pie in the sky and kids playing in the universities. So that.
And maybe I'll just also, it's kind of about the gearing, the timelines, right? So we talk of this, when there's this step, like the Moore's law, self-fulfilling prophecy of the periodicity of the steps, and then kind of recognizing that many different industries are moving at slightly different, the car industry is famously, you get a new model every 5 years, maybe 4, maybe 6, depending on the market competition in that particular segment. And you've seen some even companies stretching that timeline a little bit as they're focusing on a different approach per vehicle. But that's an example where there was a well-acknowledged thing. We're going to take a bigger step, and then we're going to take a series of smaller steps, because that's the only thing that kind of made sense. And we see then when we look at cloud and we look at edge and we look at the point of this end-to-end value creation, right? As solving a systems level problem, as Sanjay was saying, that's more economically meaningful if you're able to monetize that more directly with a certain scale of invest once, and then you can just keep kind of reselling that end-to-end solution. And so I think when we look at VLSI and the underpinnings of hardware and technology, and what are we solving on communications, what are we solving on compute, what are we solving on how that gets applied to medicine, how does it get applied to automotive, how does it apply to future fields like augmented virtual reality that are evolving incredibly quickly as we speak now, there's a recognition there's going to be a plurality of types of devices, right? Is it about virtual reality? Is it about a lightweight augmented reality glasses that's very almost imperceptible that it has compute capabilities? And then all of a sudden you bring in, well, some of that compute is distributed. So the software design of how the hardware functionality is partitioned, and that can be done more dynamically. And so in my view, the important thing is that the kind of bigger steps can still occur, and then certain of those kind of node shifts and that kind of combining of technologies, it does need to match the impedance and the periodicity of the target market. And I think that's where we've seen the race for consumer scale with a web application. How quickly can I, and we always, when universities ask me, hey, should we have all our students write an app that does some interesting little video game? I'm like, no, if you're a university student, you should be learning the hard stuff and really kind of building those foundations. So I think it's that perspective of the acknowledging there's going to be multiple parallel intersecting timelines. And then if you bring up the structure of the semiconductor industry and how things are currently partitioned, well, that's also always changing. And new companies are being formed that have unique technical capabilities. And so I think there's not necessarily going to be this one perfect solution. It's really going to be about a recognition it's a hard problem. Obviously, we're recognizing that internationally, it's also well recognized that this is important for national security. It's important for technology independence. It's important for GDP growth. And so I do feel there's been a lot of kind of relearning some of those lessons, and that important to get the kind of long time frame right. And the only way to win in the long term is also to win in the intermediate term, and to some degree make sure you're not hurting yourself in terms of your ability to execute in the short term.
If I could just go back very quickly to the EDA part of your question, which was Has the EDA industry turned out right? Well, it's consolidated. There are two guys. They have duopoly. There's no question in my mind. They've decided they will capture 3% of the revenue of the semiconductor industry. That's it. They've decided. You know how it is. They have volume purchase agreements. Essentially what they're doing, they're looking at your revenue every year, and they're determining what's the 3% of it, and they believe that's their natural right. And that's what they get. And if you look at their market cap combined, it's actually something like 7-8%. They get higher multiple. There's more certainty. You know why? They don't care if your chips sell or not. They're going to get their 3%. Because the tool business is always higher multiple than the diagnostic and market business, right? I would say, have they done right by the industry? Probably. Only because if I look at software industry, it's so awful. I mean,
I've got my students in the audience.
Well, no, I know, but Charlie and I would do chips, and we will find out that there was a bug, and guess what? We would rev our chips faster than the software guys could rev and go through the bug reduction cycle and all of that. Because now I think there is a lot more mechanistic ways because of open software and because of cloud where software can be developed better. But remember, we worked in a software where it was embedded software. It wasn't internet software where you can do canary releases. We had to make the software work before we released it. So our software threshold was much higher. And I did not see any tools to make software faster and better and testing faster and more deterministic, more formal ways of testing. But guess what? VLSI design got much further. So I as much as I don't like the fact that they actually, the worst thing I don't like about them is they kill the innovation from small companies. What they're doing is, for small companies, you still have to pay $1 million to buy a tool. And that I don't like. But I do like what they've done for the industry otherwise.
Let me just drink from this mug for a moment.
But there's nobody here. I know the two CEOs, they're not here, so I can say what I...
No, this is a DARPA-funded project.
Oh, okay. All right.
On open source EDA. That Qualcomm was a part of, actually, a subcontractor to UCSD. So let's try to wrap up. One small comment is, 3% used to be 2%, and it's become 3%.
Oh yeah, and it'll go to 4%.
And the consolidation and maturation of these industries, the 60-year trajectory of Moore's Law, I mean, this is almost inevitable, what's happened. I just wondered if there was a miracle solution that you could propose in real time. You've got a range of folks from Erwin Jacobs to Charlie Persico, Marty Cooper, Dean, Peter Asbeck, and then young people at the back. Any parting thoughts on the topic? You know, we had a VLSI revolution. We're living it. There's this incredible long tail and cloudy future in so many dimensions. Any parting thoughts for the audience? You know, what should people go home and think about?
I mean, I guess I would just, that it's okay that it's complicated, right? And I think there's that reality that there's no simple solution to this interaction between technology progress and application use case and government relative to industry and public-private partnership. I think what's important is to keep trying creatively to solve problems that have impact. And I think that kind of boils down to even finding it interesting. We were talking to some of the students just before today, just before this talk started, on thesis topics and what are they focused on. And if you're focusing on something hard and interesting, then you're doing your part, because it's that training even how to solve a problem and recognizing there's going to be 30 or 40 or 50 problems in your future, and they're only going to get more multidimensional. Bring in the economics, bring in timelines, bring in economic realities, macro conditions. And so it's that perspective of being resilient and do your homework, and that mixture of keeping your head down and at the same time looking up.
I'd just add that where we're headed now in computing is solving unstructured problems. So we have huge number of sensors with vast amount of data, and we're trying to make real-time decisions at the edge on that data. And that requires a complete new evolution of sensors with all the things that we talked about, magnetics, RF, and the entire spectrum. One of the things, example I could give you is that when you have a back surgery, you have at the moment 70% chance of success. And part of the reason is that there are lots of nerves along your spinal cord, and you necessarily take a lot of care not to hurt those nerves, and therefore the surgery is not very successful. But those nerves absorb a different frequency than fat does, than muscles do. If we could have sensors which can isolate all of these things, then we could make that surgery 80%, 90% successful. So I see complete explosion in sensors. We are now beginning to interact with a much more complex world in our computation, and we're trying to automate it. So that I feel that sensor world is going to explode, and of course, if you want to make sense of it, then you can't process it using von Neumann. You'll have to use some AI kind of structure, and if you're going to use some AI kind of structure, then you need to become more power efficient and more dense. Those are things that I see looking forward.
So first off, gentlemen, thank you all very, very much. John, we know it's very busy for you, and we're grateful you spent some time with us. Sanjay, I know you're very busy too, and of course, Professor Mead, it's so great to have you with us. You know everyone's enjoying that you're here. Andrew, thanks for sitting on the hot seat. You're the one that had to make all this work. And you know, you herded the cats pretty well, I think. What do you think? Yeah? All right. So let's have a round of applause.